Hello again, geometry students, and welcome to lesson for 5.6. And just one really new thing to learn here, something called indirect proof. So we're going to talk about that in this lesson. Make sure you're using those extra examples in your book to help you with the things we're doing here. So let's start off with a definition of what indirect proof is. So indirect proof, we've done direct proofs. Now we're going to do something called an indirect proof. So a proof, an indirect proof is a proof in which you prove a statement is true. That you prove a statement is true by first assuming its opposite. That's the key part here. You first assume its opposite is true, and then arrive at a contradiction. So opposite and contradiction, the key parts here, in my opinion. So you assume the opposite is true and then you arrive at a contradiction. So you've got something that's true and not true at the same time. That means what you started with can't be the case. So thereby proving the original statement true. Now if you've never seen an indirect proof and you just read that, you're probably like, I really want to see an example of this. I don't quite get what you're saying yet, Mr. Wagner. So let's check out an example. And for this, let's draw a triangle. You can just do these freehand if you'd like. If you want to use a straight edge, you can. I don't want to use red yet, or right now, so let me get that in black instead. So I'm going to draw a right triangle. It's going to be triangle ABC. We'll just keep it simple here. So there's my right angle. This is going to be A, B, and C. And then at this point, I'm going to use a different color. I want you to use a different color for part of this, for the parts that I use a different color for. So this is going to be an indirect proof example. So please write that in a different color here. This is an indirect proof example, and I'm going to give you this stuff as true. So the stuff in black, just write in your pencil. You are going to be given this right triangle that you see over here, right triangle ABC, and we're going to try to prove that this is the case, that triangle ABC does not have more than one right angle. So indirect proof, I think, is the easiest way to actually prove that this has to be the case. We know from before that the triangle's angles have to add up to 180. And if you had two or more right angles, that would mean, let's assume that these two are right angles, A and B, those would add up to 90 themselves. And then this other one has to have some sort of measurement to it. It can't be 0 because then it's not a triangle anymore. So you'd have 180 plus something that's not 0, which would be 180 and some change at least 0.001 or something like that. So you wouldn't have a triangle anymore. So that's kind of where I'm going with this. Off to the side here, I'm going to draw a triangle in a different color. In my orange is what I'm using here. So we're going to, off to the side, we're going to assume an impossible picture, basically. We're going to assume that this is true to start. Oops. we're going to assume this will look a little funny, but yes, we're going to assume that that's true. So I've just taken my triangle, kind of rotated it over here. We're going to assume that this is A, B, and C. The contrast of that isn't sticking out very good, so let me change the colors on that. That's better. So this is standing out a lot better. Still using this. You can use the same color for the orange and the red. Just I did this in red so it would be easier to see. So assume this. We are assuming the opposite of what we're trying to prove. We're assuming that it does have more than one right angle right here. So this, we're going to assume the opposite. Let's put this here in black. So this is in your pencil again. So we're going to assume this is true. And so our proof, we will start off by assuming the opposite of what we're trying to prove is actually true, even though we intuitively got this sense that it won't be. We're going to start with that. So first assume triangle ABC does, so let's put this, add this in a different color here. And notice we're assuming the opposite. So assume the opposite. Please put this in a different color so that it stands out and doesn't get mixed up with your actual proof itself. So we're assuming the opposite is true right here, that it does have more than one right angle. So assume this does have more than one right angle. So that's our assumption in this red picture over here. It's a comma, not an exclamation point. There we go. So let's assume it has two, which is what we've done over here. So that would be the opposite of not having one. It would actually have, or not having more than one, it would have more than one. Let's assume it has two. And we'll say those two are, like we said here, angle A and angle B. And so we verbally went through how we're going to go through this proof already, but now we have to just write that down in a formal way. So doing a paragraph proof here. Notice this is not a two-column proof. Paragraph proof working, I think, a little better for this indirect proof here. So we can assume, we know then the measure of angle A equals 90 and the measure of angle B equals 90. That's what right angles are. So if I were to have to give a reason for that, let's put that here in parentheses next to the end of each thing. So this is a definition of a right angle. Tell me that they add up to 90, okay? And so this means measure of angle A plus the measure of angle B would equal 180. 90 plus 90 is 180. You could say we just combined like terms, or we could just say simplify, something like that would be sufficient for a reason for that. So I'll just put simplify. And we also know that triangle sum theorem from before. You add up the three angles in a triangle, it adds up to 180. That's supposed to be the case. So for triangle ABC to be a triangle, it must also be true that the measures of all three angles add to 180, 180 degrees. So if A and B add to 180, and all three are supposed to add to 180, this means that the measure of angle C would have to be 0 degrees. Be the only way that would be true. However, angle measures in a triangle must be greater than 0. You can't have a 0 degree measure in a triangle because then you don't have a triangle anymore. So it must be greater than 0 degrees. So we got a contradiction there. So let's write that down. So we have a contradiction and therefore our original assumption must be false. So we assume that they did have more than one right angle, or we assume the triangle had more than one right angle, and then we arrived at something that can't be true. We had a contradiction to a theorem from before, the triangle sum theorem. It contradicted the triangle sum theorem, which we knew had to be true, and so our original assumption could not be true, had to be false. Therefore, triangle ABC cannot have more than one right angle. Cannot have more than one right angle. Okay, so this cannot be true. This is there's a special name for this, a reductio, I'm not sure I'm pronouncing this right, but reductio ad absurdum. It's kind of a phrase that if you want to sound really smart, this is just a proof by contradiction, an indirect proof. This has to be the case here. So let's move on to some non-proof stuff to finish the rest of this lesson and this chapter. So the Hinge theorem will go here. This will be 514. And over here will be the reverse of that, the converse of the Hinge theorem. And this, you may have guessed it, 515 is what that one's going to be. And like magic, a door appears. So I want to talk about hinges. This door is on a hinge, and this will be kind of matching up with what we did over here with example 2 in our previous notes in 5.5. Thinking of this red door, or this red part, kind of be like my door on a hinge right here, opening up and closing up. Something similar here with 5.6. So with these ones, rather than write the theorem out itself, I'm going to show you an example of how each theorem is used. So let's call this example 2. We'll call this one example 3. So you can draw, I won't use different colors on this one. I will just draw some triangles in here. You can use a straight edge if you'd like to. If you want to just go freehand with this, it's okay too, but just make sure you make it look as best you can like the triangles I have here. We're going to say that this angle measure is 105 degrees right here, so I'm going to try to make that a little bit more than 90. We'll go with something like that, and then this other one I'm going to make 75 degrees. So here's 90, go about 15 degrees. Instead of 15 degrees out this way, I'm going 15 degrees this way instead. And making another triangle. I want to make this side be the same length as this side right here as best I can too. So I'm going to say right about there. And then I'm going to add some marks into the picture. I'm going to say that this and this are congruent. I'm going to say that this and this are congruent. So if you didn't draw your picture in such a way that those look congruent, try to fix that for me at this point. So pause if you need to fix that. And let's say this is 105, this is 75, and we'll give these vertices some labels. This is going to be R, S, and T, and this is going to be V, W, and X. So you should notice here, why is this called the Hinge theorem? Well, this, I basically just imagine this on a hinge. I kind of closed that up here, and so that's what I did. From here to here, I closed it up. I'm going to draw as a hidden line, do the same thing on yours, how this essentially was like a door on a hinge. So this is what I had to start right here. if I connect this to this to this, I have the same triangle as what I started with over here. So this door on the hinge, this side closing up here. Let me demonstrate that to, well, no, I can't do that with that, but this side is just closing up here. I'll erase this in a second. So notice how these triangles would be the same like that, but I don't want to get rid of those marks. I just want the ones right here. So that's what I'm saying there. And so which of these sides, we have two corresponding sides that are congruent. So I'm going to say that first. This has to be the case with two corresponding congruent sides. So I double underline with, that's pretty important. If you don't have two corresponding congruent sides, this doesn't work. But if you do, we can say, I think a better way to say this is, since the measure of angle S is greater than the measure of angle W, what has to be the case? The sides across from these angles have to be matching up in such a way that this side is bigger than this side, because this triangle closed on the hinge, in a sense, this side closed up. This has to be the case. So since this is true, then TR or RT must also be bigger than VX. So basically start off with a triangle, two sides that can't change. This side and this side are the same. You close that up, the angle gets smaller, the side gets smaller. So you open it back up. If you went from this to this, if the angle gets bigger, the side gets bigger without the sides changing length. So that has to be the case here. So this is going to be true. And now something similar over here. Let's draw another triangle. This one I'm going to make look kind of like a right triangle here. First one right there, okay. And then I'm going to draw another one in like that, but I want you to imagine this being my hinge right down here. The door is right here. The door is closing, so it's going to come this way. So in a sense, this is closing here. I'm going to erase these lines in a second, but this door is closing. We're going to have something closing up like that. So this closing this way, we're going to draw a triangle that looks kind of like that over here. And so I've got something like this. And now I want this length to be the same here as this bottom length is over here. I also wanted this not to change from here to here, so I want that length to be the same as well. So I'd say right about there should do it for me. See if I can extend that out just a little bit that way. Okay, so that's a little better, I think, there. And I want to get rid of these hidden lines here. And I'm going to put them in this picture over here instead. So these ones I do want you to draw. So this door, this was like my door right here on the hinge. It was closing up a little bit here, and it used to be right here, but we closed that door. We're starting to close that door, and we're going to say this is triangle A, B, C right here. This side and this side being the same as this side and this side over here, and this is triangle D, E, F right here. So if you look at that, and we would say that this is 8 and 5, we still have two corresponding congruent sides again. So let's write that down to start. So with both of these theorems, the Hinge theorem and the converse of the Hinge theorem, you have to have two corresponding congruent sides, otherwise it doesn't work. So if that is the case, you can say that in this example, since AC, you look at that, is that bigger or smaller than DF? It's bigger, it's more. So since AC is bigger than DF, it has to be the case that the angle across from it, angle B, and it looks like this is true in the picture too, but you can't always trust the looks of the picture. You got to trust the numbers that are there. Angle B, the measure of angle B, is going to be greater than the measure of angle E. So that's the case. So essentially what the Hinge theorem and converse of the Hinge theorem boil down to is you got two sides that match up. Two sides that match up. The angles in between them, the included angles, if it gets bigger, the side across from it gets bigger. If it gets smaller, the side across from it gets smaller. Over here, if the side across from it is bigger, the angle itself is bigger. If the side across from it is smaller, the angle itself is smaller. Good little recap of what we just did there. And so let's check out a fourth and final example, just drawing some pictures in and deciding whether these things are equal to each other, less than, or greater than. So we're going to complete each one of these with a greater than symbol, a less than symbol, or an equal to symbol. And so let's draw some pictures in here. Start with something like this. So I want you to draw two right triangles as best you can. And I want you to try to make them look, in this case we're going to try to make them look congruent. I'm not going to say that they are at this point. I'm not going to say that they're not at this point. Just going to draw those in. Not my best work there, but I hope you get the point there. That's what we're going to say is a right angle. We're going to say this is angle 1. This is congruent to this side, and the hypotenuse congruent to the hypotenuse. So you notice here's 2. I also want to label that there. Do I have the included side? In a sense, it's like side, angle, talking about the side, this angle, and the side here, but we're not saying now that the triangles themselves are congruent. I'm just trying to figure out what's true about the angles. So I have a little blank space here. Measure 1 compared to the measure of angle 2. What goes in between here? Different color. Take out your different color, because we're not going to say this is true to start. We're going to say that this is the case by this. So what is the case here? Well, can we actually prove that these triangles are congruent? Yes, we can. If we go back to the 5 congruence postulates and theorems that we learned from before, we had side, 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 angle, side, angle, side, angle, 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 side, and then this one, hypotenuse, leg. We have a right triangle, we have a right triangle. So these have to be equal to each other. Put that in a different color. This is my reason why I put this in a different color too. This is the hypotenuse leg theorem. So if you had to give a reason, that would be your reason. This is your answer to the question up here. That would be your reason. So let's draw a couple more triangles. And with all of these, I want you to make them look congruent. We're not going to say yet whether they are or not, but I want you to make them look like that they actually are. The book is going to try to throw you off sometimes. You might see something on a test or a quiz like that. So let's draw that, and I'm just actually going to make a duplicate copy. And so I want you to do as best you can the same thing. You can't just copy and paste though on your writing, but you can draw triangles that look the same. So we're going to say that that's the case here. I want to bring this down just a little bit more so I have some room to write some things in here. So I'm going to tell you that this, no, I want that in black. So the stuff in black we're starting with being true, that this is the same as this one over here. This one's the same as this one over here. And I'm also going to tell you that this is angle 1, this is angle 2, and this one's 15, the side length is 15, that side length is 13. So what could you say about the measure of angle 1 compared to the measure of angle 2 in this case? We look at that, go back to your Hinge theorem. This one we don't have side, angle, side, or any of those things where we can say the triangles are congruent. We actually have different side lengths. So this would be like side, side, but these two sides are not matching up. So if you said side, 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 no, because these sides aren't congruent. So what was true? We look back at this. If you have the bigger angle, that means you have the bigger side across from it. If you have the bigger side, that means you have the bigger angle across from it. So this is more the converse of the Hinge theorem. So we're taking the bigger sides is going to have the bigger angle across from it. Even though it doesn't look like it, we purposely did that just to hopefully focus more on the theorem. What's the theorem say? So this side is bigger than this side, therefore the angle across from it is bigger than the angle across from the smaller one. So this one, measured angle 1, must be greater than the measure of angle 2. Put that in a different color. And what's the reason for that? That's the converse of the Hinge theorem. If you said theorem 515, that would also be correct, but I think calling it the converse of the Hinge theorem is a better way to state that. So this, kind of like one of these doors being on the hinge, this would actually be smaller, this angle, because the side itself is smaller. And so let's write one more thing under there. Converse of the Hinge theorem, since 15 is greater than 13. So we could say that that's the case. And that's still theorem 515. So put that in there. And then finally I want to draw a couple more triangles. These ones are going to share some sides. So automatically when you see something like that, you should be thinking a certain property that we learned. Let's see if you remember that property. So I'm just going to take that, make a duplicate copy in just a second. I'll just pause it for a second. There we go. So I just drew my triangle here, and then I drew the exact same triangle just mirrored in this x-axis up here, and I'm going to label some things in the picture. Let's call this W, not in a different color. There we go. This is stuff that's true to start. W, X, Y, and Z. And I'm going to tell you that this is true to start. That this and this are the same. I'm going to tell you that this angle measure is 38 degrees and this one's 41 degrees. So how do we use the Hinge theorem or the converse of the Hinge theorem? Let's go back here. We have to have two corresponding sides to start, corresponding congruent sides. If we do not have two corresponding congruent sides, it doesn't work. We might be using this one because we're given the angle measures this time, not the side lengths. So we're given the angle measures here, but do I have two corresponding congruent sides to start? Were the angles in between those sides? Well, initially you might look at that and say, no, I don't know that this side is congruent to, oh, wait a minute, what? Oh, no, I do know that that side's congruent to that side, huh? Yes, that's what I was getting at. There we go, the reflexive property, making its comeback in lesson 5.6. It's been a while, reflexive property. Nice to see you again. How you doing? How are the kids? How's the symmetric and transitive property? How are they doing? They're doing good? Oh, it's good to hear. Okay, so what angle is bigger? This angle is bigger. So what side is bigger? This side is bigger. So we have two corresponding congruent sides. The angle in between them is the one in question, or the one that's different from here to here. So this is going to be the case with this one. We want to say not the measure of the angles now, but we want to compare the side lengths. So XY compared to, I'm not going to fill that in quite yet, but almost ready to do that, compared to ZY. Which one's actually bigger? Different color for this, take that different color out here. Which one's actually bigger? Well, it would have to be the case that the bigger angle goes across from the bigger side, the smaller angle, smaller side, so YX or XY must be greater than ZY. And so what theorem is this, or what did we just use there? We used not the converse of the Hinge theorem because that has the sides instead, but the Hinge theorem itself. So this is 514. We used the Hinge theorem. So this is the Hinge theorem. Since, what was the case here? Since 41 was bigger than 38 degrees. That's theorem 514. Okay, so the different colored stuff, do that in a different color on yours. And then I just want to give you one final hint on your classwork. If you have to do this one, this may or may not be assigned, but if it is assigned for help, write this down for me to be the last thing for your notes for this lesson. For help with number 29 on the homework, or if we're doing it in class, the classwork, see example 4 on page 304. So I'm not going to go over one like that. There's a good example in your book there on page 304 to look at to help you with number 29 on the classwork if you need that. So hopefully that will help you a lot in your tackling of the problems for this new lesson for 5.6. Let me know in class if you have any questions. Thank you.